Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an Associate Professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about the resistor color coding and the concept of impedance and admittance. So first of all, let us discuss about the resistor color coding. So as we know, in the laboratory, we usually do the experiments in the circuits so that we will connect the various resistors in series or parallel combination so that we can find the voltage or the current across or through any element. So here it is very important to find the value of that particular resistor by using this color coding, because as we can see, the resistors having a color bands on it, so that the color bands having the various colors, okay, right, as you can see here, the black, brown, red, orange, yellow, green, blue, violet, grey, white, gold and silver. So these colors you can see on a resistors, and by using these color coding, so we should able to find the value of that particular resistor. So what is that value of that particular resistor, which means what is the resistance of that particular resistor by using this color coding value. So here, as you can see here, for every color there is a value and there is a multiplier, and as well as there is a some tolerance. Of course, here as you can see, some colors they are having some tolerance value and some colors they don't have, but most of the colors they don't have the tolerance value. Only the red color having 2% of the tolerance, and the remaining gold and silver also having some amount of the tolerance, which is the gold is around 5% and the silver is about 10% of the tolerance value is there. So tolerance is nothing but the plus or minus that particular value. Okay, so it means it is not exactly that particular value. So which it may be a plus or minus 5% of the total resistance of that particular resistor. And if it is a silver, then there is a chance of 10% of plus or minus of the total resistance of that particular resistor. Right. So here, as you can see, there are, let me see here, 1, 2, 3, 4, 5, 6 different types of resistors are there. So the 6 resistors having the various resistance values. So each resistor having its own resistance. So why? Because here these resistors are designed to have a particular resistance value, and the resistance value is indicated by this color coding. So which means we can identify the resistance of that particular resistor by using this color coding. As you can see here, these 6 resistors having the different combinations of the colors. Okay, of course here all these 6 resistors having the combination of these colors only that here we have mentioned. So here let us come with first resistor. Here the first resistor here, what is that? Here it is start with some orange color, red or orange color, and here it is some gold color, and here it is again gold color, and here it is brown color, and here it is red color, and here it is again gold color, right? And of course the number of bands for each resistor is also may be similar or may different. Let us see here the resistor 1 here having 1, 2, 3, 4 color bands is having, and again the resistor 2 also 4, 3, 4, yeah, of course. So most of the resistors here having the 4 color bands, but here sometimes there are some resistors having more than 4 color bands also, that we will discuss how to identify the resistance of that particular resistor by using this color code, right? So as you can see here, for every color having the various values, which means here as you can see, start with the black, here it is 0, and brown 1, red 2, and orange 3. So like that, as you can see, up to white here it is 9. And when coming to the multiplier, okay, so of course these these colors having the value as well as the multiplier. So here the multipliers are here, which means here 1, so which means here 10 to the power of 0. So this 10 here it is nothing but 10 to the power of 1, here it is 10 to the power of 2, and here it is 10 to the power of 3, and here it is 10 to the power of 4, which means as you can see here 0, okay, 0 and 1, 10 to the power of 1, the multiplier. So 2 means 10 to the power of 2, and 3 means 10 to the power of 3. So like that here 10 to the power of 5 and so on up to 10 to the power of 9, right? And the tolerance, of course, here only the three colors having the tolerance. One is red color, which is 2%, which means plus or minus 2%, and the gold here it is 5%, which means the plus or minus 5%, and the silver here it is the 10%, which is plus or minus the 10%, right? Then coming to here, as you can see here, these are the three different types of resistors that we can see. And the first resistor is having the 4 color bands, and the second resistor is having 5 color bands, and the third resistor is having 6 color bands. In generally, most popular, mostly we use the 4 color band resistors only. Okay, the 5 and 6 color bands resistors also sometimes we may use. Okay, that I will let you know. So here, of course, here the color, here as you can see, where you are having, because the tolerances are having only the 3 tolerances that we are having, as you can see here, one is the silver, another one is the gold. Okay, so here if it is a silver and gold is there, so suppose let us consider here it is let us consider here it is some it is a silver color. Okay, but of course don't get confused again, it is looks like what is that, the gray color, but let us consider here it is because of this the color formation. Here it is looks like the gray color, but let us consider here it is a silver color because here it is a silver color. So the immediate the band which is what is that, immediate to the silver or gold color is the multi. Okay, so the band, the color band which is immediate to the silver or gold color is the multiplier. So which means here this is the red color is there immediate to the silver color. So here the red color means here, as we know, the red is the 2. Okay, and because this is the multiplier, so multiplier means 10 to the power of 2. So which means here it is 10 to the power of 2. And before that here there is a pink color, but actually this is not exactly the pink here because here 7 is there, so 7 is the violet, but it is looks like the pink, but here it is a violet. So this 7, here it is a 7. Okay, and the yellow color is 4, so here it is 4. So which means here 4700, which means here 4.7 kilo ohm, and at the tolerance of the 10%, because here the silver is there, so that's why it is the tolerance of 10%. So here, which means here it is 4.7 kilo ohms. This is how we can identify the resistance of a particular resistor, right? Then coming to the second one. Okay, so here, of course, here the 5% tolerance is there, so this means gold. Actually, of course, here it is looks like the what is that, some kind of yellow mixing, but here it is, let us consider here it is gold. This is gold. So either you can start from right side or left side, whatever it may be, but the thing is the immediate what is that, the band to the gold or silver is the multiplier. So again here it is red is there, so which means here it is 10 to the power of 2. And let us start with here. Okay, so this is blue color, so blue here it is 6, here it is 6, and then after that here the gray color is there. Okay, so which means here the gray color is 8, so 8, 6, 8, and again here what is that, the black color is there, so black color is 0, 6, 8, 0, and then red, because this is immediate to the what is that, the gold color, that is the tolerance color, so that's why here it is the multiplier. So the multiplier for that red is 10 to the power of 2, so into 10 to the power of 2, so which means 680 kilo ohms. This is 680 kilo ohms. Sorry, 68 kilo ohms. So this is how we can find the resistance of a particular resistor by using this color coding, right? Then coming to the third one. This is a 6 band. Okay, so again here in the 6 band. Okay, so let us see here 560 kilo ohms. Okay, this is which color here it is, this is orange color. Okay, so that's why here again this is the temperature coefficient here in the 6 band. Okay, the final the what is that, the color code, okay, which is placed on this particular band. Here it is the temperature coefficient. So because here it is red, so here the temperature coefficient of that, here it is 50, and then after that here the before that one is the tolerance again. Okay, so here for the tolerance here it is 0.1%, and before the tolerance here you are having what is that color before the tolerance of this particular band. Before the immediate band which is immediate band to the tolerance, here it is the multiplier. So here the color, here it is the orange color. So here orange means here 3, which means 10 to the power of 3. So which means here 10 to the power of 3, 10 to the power of 3. And before that, which color is there? Black, here it is 0. And before that again blue color is there. What is the blue color? Here it is 6. And again before that green color is there. What is the green color? 5. So 560 into 10 to the power of 3, or in another words 560 kilo ohms, okay, at the tolerance of 0.1%. Okay, but don't get confused here. The tolerance here, which are having only the gold and silver, but not the brown, something like that. But here, these are the very commonly used, colors which are having the tolerance. Okay, but particularly here, these are also, some other colors also having the tolerance. Like here, as you can see, this red is also having the 2% of tolerance, and green is having 0.5%, and the blue is 0.25%. But here 0.1, 0.25 and 0.5 are negligible. So that's why even 1% is also negligible. So that's why here we did not mention the tolerance value. Okay, so the tolerance which is having more than 2% only here we have mentioned. Okay, don't get confused again, because here only these 3 colors having the tolerance value. Okay, all others not available, but here the other colors also we have mentioned. Okay, don't get confused, because here it is 0.5 and 0.25 is very less when compared to this 5% and 10%. Even though here the brown color is also 0.05%, so which means it is negligible. So that's why we didn't consider. That is the only reason that we didn't mention, that I didn't mention here. Okay, right. So this is the way to identify the resistance value. Okay, so suppose here, as you can see, suppose if you want to find the color coding of that of these particular, the resistance value of these resistors. Okay, so try to identify the value of that resistance of these 6 resistors. Okay, so that you will get understand how to identify the resistance of a particular resistor by using this color coding, right? Okay, this is all about the identify the resistance of a particular resistor by using the color coding. Of course, by using the multimeter, we can identify or we can measure the resistance of a resistor, but it is, the basic knowledge is required, because without the multimeter also we can able to find the resistance of a particular resistor by using this color coding, because that's why, as you can see here, every resistor having some different combination of color bands. So these color bands indicates the resistance of a particular resistor. Now we are going to move into another topic, which is the concept of impedance and admittance, right? So before going to that, let me discuss some basics, because already we have already discussed some basics related to the impedance, admittance, and the power factor and all, or the phase angle between the voltage and current. So these all topics we have already discussed in the introduction to AC quantities, which means alternating quantities. So here just to extend the topic, so here we are going to discuss about the another concepts of impedance and admittance. These are based on the introduction to alternating quantities only. So as you can see here, there are, let us consider here it is a triangle. Okay, so we usually call it as a power triangle, that we will discuss later. So as you can see here, this side, let us consider here the angle between these two sides. Here it is theta. Okay, and this is the adjacent side, and this is the opposite side. So, and this is the hypothesis. And adjacent side here, let us consider here it is x, this is, and this is y. Okay, so because this point is x and y, and here let us consider here it is r. Okay, so as we know here, r is equal to square root of x square plus y square, and theta is equal to here the tan inverse y by x. The theta is equal to tan inverse y by x. What is that here? Yeah, here it is x by y. Then if you want to find x value, then x is equal to r cos theta and y is equal to r sin theta. So actually why we are discussing these things means, so here the alternating quantities are represented in terms of, because as we know, the AC is having both magnitude and as well as the direction. Okay, both magnitude as well as the direction. Unlike in AC, the DC is having magnitude and as well as the polarities. But here these AC quantities having both magnitude and as well as the direction, which means here we are representing in the form of vector quantities. So the vector is having both magnitude and as well as the direction. So that's why in the vector notation is represented in two different types. One is the triangular form, another one is the polar form, right? So this concept is where we are discussing, okay, how to convert the triangular form into rectangular form and rectangular form into triangular form, right? So which means here, as you can see here, this is suppose if you want to represent in a triangular form, so x plus jy, okay, or in rectangular form r at an angle of plus or minus theta, right? So here r means here what is that? R means here it is square root of x square plus y square. Okay, so which means if you know the x and y values, then you can find r value, and theta is equal to tan inverse x by y. So like that here, and suppose if you know what is that r and theta value, then you can find x and value by using these equations. So which means the triangular to rectangular to polar and polar to rectangular form. So this is the rectangular form and this is the polar form, right? Then now, yeah, the representation of the rectangular and the polar form here. So this is the rectangular form, z is equal to x plus or minus y, z into y. So which means here this x is the real term and here the y is the imaginary term. Okay, we usually call it as a x is the real term and y is the imaginary term. Then similarly, if you want to just convert this rectangular, or if you want to represent in the polar form, then z is equal to r at an angle of theta. Okay, so here theta is the angle between x and y. Okay, so that's why here then another form here is also there, that is trigonometrical form. So z is equal to r cos theta plus or minus z sin theta, and another form is the exponential form. So exponential form here again r e to the power of plus or minus z theta. Then as we know already how to convert this rectangular into polar, polar into rectangular form, just now we have discussed. Okay, so which means if you know x and y, then we can find r, because r is equal to square root of x square plus y square, and theta is equal to tan inverse y by x. Okay, so not x by y actually. Of course, here because in the previous case we have represented in a different way, and here we are representing in a different way. So tan inverse y by x. And suppose if you know r value, then r and theta value, then you can find the x and y values also. Here x is equal to r cos theta and y is equal to r sin theta. So this is the way to convert what is it? Of course here r is also same, what is r this way, and here also theta is same, that theta is tan inverse y by x. Okay, don't get confused. This r and this theta is same. So that by using these equations we can convert the polar into rectangular and rectangular into the polar form, right? Now we are going to, there is another notation called J notation. Okay, so which means the J operator is we usually call it as a vector operator. Okay, that's what here, just now we have seen the J. Okay, so we can also this one represented, call it as the rectangular, right? So what is this J notation here? It is nothing but, as you can see here, suppose at 0 degrees, okay, 0 or plus or minus 360, because if it is, let us consider here, if it is 0, then again if you come from 0 to and again 0, then which is 360 degrees. So here it is, as you can see here, you are having, let us consider this is the real axis and this is the imaginary axis. Okay, so if theta is equal to 0, you are having only the real component and the imaginary component is 0, right? So that's why here, as you can see, real is, and the real is also positive and imaginary is 0, because 0 means, the 0 is 0, we no need to consider whether it is plus or minus. So that's why here 1 plus j 0. And here if it is 90 degrees, which means plus 90 degrees, okay. So here if it is plus 90 degrees, then the real term is 0, but the imaginary is having 1. Okay, so that's why here plus j, and this is again the positive. Okay, so that's why here 1 at an angle of plus 90 degrees or 1 plus j 0. And then when coming to the minus 90 degrees, okay, so minus 90 degrees is nothing but here are what is that, minus 90 degrees or the 270 degrees. Okay, so minus 90 or the 270 degrees, because if you go this way, it is plus 90, then if you go the opposite way, then here it is the minus 90 degrees. That is the only way. Okay, so minus 90 or here it is 270 degrees. degrees. Okay, both are same. So minus 90 means again here it is the imaginary is my negative sign. So that's why you will be having the only the imaginary part which is negative and there is no real part, right? And then when coming to the plus or minus 180, of course here it is 180. 180 is having only the real part which is negative real part. There is no imaginary part. So that's why here it is minus 1 plus j0. So this is how the j notation. Okay. Now here I have just mentioned some examples for your practice purpose. Okay. You can just go through and convert these. What is that? First one is this is the rectangular form. So convert the rectangular form into polar form. So which means here polar form r is equal to square root of 5 square plus 10 square and theta is equal to here tan inverse 10 by 5, right? And similarly here it is r is equal to what is that 10 square plus 3 square and theta is equal to here tan inverse minus 3 by 10, right? Because here it is x and here it is y and here also it is x and here it is y. As we know, r is equal to square root of x square plus y square and theta is equal to here it is tan inverse y by z, y by x, right? So that is how you just substitute, and of course here it is polar form is there. So which means x is equal to r cos theta and y is equal to r sin theta, right? So which means here r cos theta, r is here 11.18 and into cos theta here it is 63.43 and similarly here y is equal to r is again 11.18 and sin 63.435, right? So like this you can convert the polar into the rectangular form again, because now you know x and y values. Then the what is the rectangular form is x plus or minus j y. Okay, so now you know the value of x value and the value, the value of the y. So you can substitute here, then you can convert into the polar form. And again here also, if you want to convert this one, then here it is x is equal to r is 10.44 and cos of minus 16.7 degrees. And similarly here y is equal to 10.44 sin minus 16.7. So this is how we can find. And another thing here, as you can see, we know already how to add and how to multiply and how to subtract the the rectangular forms. Okay, so suppose if it is add means simply you just need to add the real terms and the imaginary terms. So which means here z1 plus z2. Okay, so the real terms are 5 and 6. So 5 plus 6. Okay, and plus j into here the imaginary terms are 10 plus 9. Okay, so this is how z1 plus z2. And similarly z1 minus z2 also. Okay, but the thing is z1 into z2 is not like that. It is not like simply multiply the real terms and multiply the imaginary terms separately. So in this case here it is 5 plus z10 into 6 plus z9. So which means the 5 into all these things. Okay, so 5 into 6 plus z9 and plus z10 into 6 plus j9. This is the way to find the multiplication of the two vector quantities. Okay, so 30, okay, plus j45, okay, plus j60 plus here j into j square. So which means here it is minus, so minus 1. So that's why here it is minus 90, right? So then now you add just 30 minus 90, here it is minus 60, and 45 plus 60 here it is j105. So this is the z1 into z2 value. So this is how we can do. So similarly the division also, right? So this is how some practice examples for converting rectangular to polar and polar to rectangle. And again, if you want to just add two rectangular quantities or subtract to the two rectangular quantities, something like that, here we can understand better from these practice examples, right? So now we are going to the actual topic, which is what is exactly the impedance, admittance, and reactance, okay, and susceptance and conductance. Okay, so these things we will discuss here. As you can see, of course, as we know, I mean, the position of the flow of current here, we usually call it as a resistance. Okay, but a circuit here, it is having both the combination of resistance and inductance, or maybe the resistance and capacitance, or maybe the resistance, inductance and capacitance. Then the equivalent quantity across those elements? Okay, so we usually call it as a reactance. So if it is a inductor, then we usually call it as a inductive reactance, and if it is a capacitor, then we usually call it as the capacitive reactance, right? So here, as they mention, in an electronic or electrical systems, okay, the reactance is the opposition of the circuit elements, okay, to change in current or the voltage, okay, due to the elements inductors or the capacitor. That's why if it is due to the inductors, then we usually call it as a inductive reactance, and if it is due to the capacitance, then we usually call it as a capacitive reactance, right? And of course here the units for the reactance is again ohm, okay, for both the inductive reactance or the capacitive reactance, but in commonly we usually call it as a reactance. And the symbol we usually represent the reactance is nothing but the X, okay, because like resistor is R and inductor is L and capacitor is C. So like this way, the reactance we usually represent as a term X. Okay, then of course just now as I mentioned, X is the commonly a reactance, but if you want to indicate the inductive reactance, okay, then we usually represent it as a XL. So here XL is equal to omega into L, or in other words, it is called as it can be also write 2 pi f into L, because omega is equal to 2 pi f into L, right? And similarly, when coming to the capacitor, okay, so the opposition, the opposition for the circuit elements due to the capacitive element, especially due to the capacitive element, then in that case we usually call it as a capacitive reactance, and the capacitive reactance we usually represented by the X suffix C. So here the value of the capacitive reactance here, it is 1 by omega C. I mean, these all are we have already derived, okay, how we can get XL is equal to omega L or 2 pi FL, and XC is equal to 1 by omega C, or because again here omega is equal to 2 pi F, so which means 1 by 2 pi F into C. So this is the capacitive reactance, right? So this is all about the reactance or the inductive reactance and the capacitive reactance, right? Then the concept of impedance and the admittance, right? So just now as we have discussed, suppose if you because the two resistors are in series, then we can simply say R1 plus R2, okay, R in parallel, then R1 the two resistors are in parallel, then we can say the equivalent resistance is equal to R is equal to R1 R2 by R1 plus R2, or in other words 1 by R is equal to 1 by R1 plus 1 by R2. But here suppose if you are having a combination of resistor, okay, which is resistor and the inductor, then what is the equivalent opposing force across these two elements? Okay, so then that is called commonly call it as a impedance. Okay, so because the impedance is defined as the ratio of sinusoidal voltage to the sinusoidal current. Usually the impedance is ratio of the sinusoidal voltage to the sinusoidal current. Okay, so which is nothing but the same like in a resistance. Resistance is equal to V by R. Okay, but impedance is the sinusoidal voltage by sinusoidal current. Okay, so then which means the total opposition force, okay, offered to the flow of sinusoidal current is called it as a impedance. And of course here the units for the impedance is also again ohms, right? So the impedance for the series resistive and inductive, so which means let us consider here the resistance is R and inductance is L, or in other words, because the symbol here it is L, but in this case it is the inductive reactance. So inductive reactance we usually represent it as a XL. Then the equivalent impedance between these two parameters here it is Z is equal to R plus JXL, right? Or in other words, okay, because into the polar form, because usually this term is called as R and this term is called as theta. So which means here R at an angle of theta. Okay, so in the rectangular form here we represent Z is equal to R plus JXL, and in the polar form we represent R at an angle of theta, and R is equal to square root of R square plus XL square, and theta is equal to tan inverse XL by R. Then suppose if you are having a resistor and a capacitor are in series, okay, again the resistance of the resistor is R and the capacitive reactance is XC. Okay, then the total impedance across these two elements, here it is R minus JXC. Okay, R minus JXC. So, or in another words, again similarly, Z is equal to something, this polar form, square root of R square plus XC square at an angle of tan inverse minus XC by R. Okay, and suppose the three combinations are there, which means the resistor and inductor and the capacitor, right? So here the resistance is R and inductive reactance here it is XL and the capacitive reactance is XC. Then the total impedance across these three elements Z is equal to R plus J into XL minus XC. Okay, because here why only always because here the inductor and the capacitor having the imaginary terms, because as we can see, okay, the angle between the, I mean, if there is a resistor, okay, then the what is that, the phase angle between the voltage and current, if it is a pure resistive load, then the phase angle between the voltage and current is zero. So that's why this term, it doesn't have any imaginary term, so there is no angle. Okay, so that's why the resistor is always the real term. But here the capacitor and what is the inductive, okay, the capacitive load, and in case of inductive load, the phase angle between the voltage and current is not zero. Okay, so definitely there should be a some phase angle between the voltage and current when it is a inductive or the capacitive load. So that's why these two are the imaginary terms. So that's why here the Z is equal to R plus J into XL minus XC. Okay. The concept of admittance, of course, admittance here it is the reciprocal of the impedance is called as a admittance. So which means here Y is equal to 1 by Z, and the conductance is nothing but we usually represented the conductance as a term with a Z, which means the G is equal to 1 by R. So the conductance is nothing but the reciprocity of the resistance, and the susceptance is nothing but the reciprocity of the reactance. Okay, so which is represented by the capital B. Right. Then coming to the various powers in a AC circuit. Okay, of course in DC the power is nothing but power P is equal to V into I. But here in case of AC there are mainly the two different types of powers are there. One is the active power, another one is the reactive power. So here active power we can also call it as a useful power, and the reactive power, of course, we can get some power but we can't utilize that power. Okay, so that kind of power we usually call it as a the reactive power. Okay. So here the active power is, because usually the power is nothing but V into I, but here in case of AC there is a concept of the power factor, or there is a concept of the phase angle between the voltage and current. Okay, because the voltage waveform, sinusoidal waveform is there, and current sinusoidal waveform is there. Okay, so both they don't have the same phase. Okay, there is some phase difference between these two quantities. Because the phase differences depends on the type of the load which is having. So that's why here we usually having the VI cos pi is the active power, and VI sin theta or pi or sin pi is the reactive power. Okay, so then coming to the power triangle. Okay, so the combination of these two is sometimes there is another power, we can also call it as the apparent power, which is represented by S, and the active power which is represented by the P, and the reactive power which is represented by the Q. So if you consider a power triangle or the impedance triangle, so here this is the theta angle, this is the angle theta. Okay, so and the adjacent side here it is the active power, and the opposite side here it is the reactive power, and the hypothesis here it is the apparent power. So this is the power triangle, and there is a concept of power factor also. As we know, the cos theta, we usually call it as the power factor as a cos theta. So cos theta is equal to active power by apparent power, which is equal to P by S. Okay, which is equal to P by S, right? So then this is the power factor. Okay, and yeah, it is also defined as the cosine of the phase angle between the voltage and current, depending upon whether the current lags and leads voltage. Power factor is also taken as unity for lagging or leading. Okay, so because the cos, what is that? The power factor should be 1. Okay, when the power factor should be 1, the cos 0 is equal to 1. So when it will become 0, when there is no apparent power. When there is no apparent power, only active power. If apparent power is 0, then something by 0 is equal to 0. Okay, then here the cos theta value, I mean the theta value is 0, then we can, sorry. So here The cos theta is the power factor, not only the theta. Theta is the angle between the the phase angle between the voltage and current. Okay, but here the term total cos theta is the power factor. Okay, don't get confused here. And the power factor is always in between the 0 and 1. Okay, so if good power factor is nothing but if it is 1, the unity power factor, right? So this is all about the power triangle and the power factor, the active power, reactive power, and the apparent power. Okay, so in the next class we will discuss next topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.